Hello ladies and gentlemen, my name is Felix Rössler and I'm gonna give you an introduction to the dynamic simulation with digital twins of heat exchangers today. I would like to start with the question, what is a digital twin of a heat exchanger? At Linde Engineering we have three different types of heat exchangers in our product portfolio. The first is the coil-wound heat exchanger, which is used for the liquefaction of natural gas. The second is the plate fin heat exchanger, which is used for air separation units. Furthermore, we have the shell and tube heat exchanger, which is used for standard applications. Our task was now to combine the three types of heat exchangers in a generic and modular digital twin of that apparatus. There are two different approaches to tackle that task. The first approach is a purely data-driven approach, which is based on historic plant data, which is used to train artificial intelligence. The basic requirements are accurate measurements, which have been performed on real heat exchanger equipment in operation. The second approach one could go for is the development of a first principle model as the core component of the digital twin of the heat exchanger. It is based on conservation equations of mass, momentum and energy and on empirical correlations for heat transfer and pressure drop. The basic requirements are of course a large amount of process know-how and a suitable modeling infrastructure to formulate the equation system. At Linde Engineering we now decided to go for the first principle model of a heat exchanger as the core component of our digital twin, simply due to the large amount of process know-how we have within our company. Furthermore, we would like to be able to extrapolate with our digital twin beyond the normal operating range of a process plant. And the purely data-driven approach of course is limited to this normal operating range as the data is collected in that normal operating range. In order to develop a first principle model of heat exchangers which considers all three types of heat exchanger geometries, some steps need to be taken. The first step is a one-dimensional representation which is valid for all three geometries. We do this by combining solid heat capacity modules with process stream modules. Those base modules interact with each other by heat transfer and pressure drop correlations. In a second step, we now apply the finite volume discretization, which enables us to formulate the conservation equations of mass, energy and momentum on the single finite volumes. Today I would like to focus on the conservation of energy. The conserved quantity within the process fluids is the volume-specific energy ρ times E. In the solid heat capacities, the conserved energy is represented by the wall temperature Ts. Of course, we need to consider boundary conditions. For the process fluid, the boundary conditions are the ingoing and outgoing enthalpy fluxes H.in and H.out. For the solid heat capacities, the boundary conditions at the actual ends of the heat exchanger are assumed to be adiabatic. Coupling conditions need to be further considered due to convective heat transfer. The transferred heat is denoted as Q.alpha. If we have a detailed look on the energy conservation equation of a process stream, we will notice that it is built up out of three terms. On the left-hand side, we have the time derivative of the conserved quantity. On the right-hand side, the first term denotes the actual transport of energy due to convection. The second term is the source term due to convective heat transfer. If we now assume that the energy dynamics of the process stream happen way faster than the energy dynamics, for example, of the solid heat capacities, we can assume the energy conservation of the process stream to be quasi-steady. This leads to the left-hand side of the equation to vanish. We can now reformulate this equation which yields the simple quasi-steady enthalpy balance of a finite volume. The outlet enthalpy flux is equal to the inlet enthalpy flux plus the transferred heat Q.alpha. The convective heat transfer equation between solid and process stream is a product out of the heat transfer coefficient alpha, the heat transfer area A effective, and the driving force, the temperature difference between wall and the fluid temperature. Today I would like to focus on those two equations which are highlighted, as they form the governing equation system of the energy conservation equation on a finite volume of a single process stream. The solution of this governing equation system can be graphically visualized. This is done in two dimensions. The first dimension is the transferred heat Q dot. The second dimension is the fluid temperature T. First we assign the inlet fluid temperature and the wall temperature Ts. We assume that the wall temperature is higher than the fluid inlet temperature. Furthermore, we assume that the fluid enters the finite volume as subcooled liquid and leaves the finite volume again as subcooled liquid, regardless the amount of heat which has been transferred. The first solution curve we can plot in our graph is the solution curve of the convective heat transfer equation, based on the liquid heat transfer coefficient alpha Lic. The second curve is the solution curve of the enthalpy balance. As one can easily see, there is exactly one intersection, meaning exactly one unique solution for this single-phase cell. We can now extend this procedure to a finite volume which is not necessarily single-phase anymore. This can happen if the fluid inlet temperature is close to the bubble point. Then the fluid can exit the finite volume either in the liquid state or in the two-phase region. We can now again plot the solution curve of the convective heat transfer equation. This time we have two branches. The first branch, based on the liquid heat transfer coefficient alpha Lic, is valid only in the liquid region. The second branch, based on the two-phase heat transfer coefficient alpha 2-phase, is valid only in the two-phase region. Furthermore, we can plot the solution curve of the enthalpy balance, which corresponds to the temperature-enthalpy relationship of the thermodynamic equilibrium of the process fluid. There's the characteristic kink at the phase change. This time we have two valid solutions for the finite volume with the phase change. If we apply a simple numerical iterative solver to that equation system, this will yield to severe convergence issues, as the solver is going to jump between the two valid solutions. This means we need tailored solution strategies for phase change cells, which have been developed at Linde Engineering throughout the last years. In the second part of this talk, I will not focus on these tailored solution strategies in detail. I will rather focus on a case study which is an example of the application of the digital twin of heat exchangers. We will have a look at the startup of the subcooler of an air separation unit, short ASU. An air separation unit has the key components of the main heat exchanger and the subcooler. The subcooler is used to thermally integrate the low pressure column and the high pressure column of the ASU. If you are further interested in ASU operation, I recommend the talk of my colleague Robert Kender, who is focused on the application of a digital twin of an air separation unit with argon production. Let's have a look at the subcooler operation. The subcooler is a plate fin heat exchanger with 4 process stream passages. The first 2 are process streams which are retrieved from the low pressure column. Both are nitrogen-rich process streams, are gaseous and serve as cold process streams within the subcooler. The remaining 2 process stream passages are called CLOP and LMP and are both retrieved from the high pressure column of the ASU. In steady state operation, both are liquid and serve as warm process streams within the heat exchanger. Please keep the color code in mind, as all the following graphs are colored in the same manner. The first phase of the startup scenario is pressurization and cool down. On the left-hand side, we'll have a look on the pressure values and normalized flow values in the single passages of the heat exchanger. On the right-hand side, we see a 3-dimensional visualization. The actual temperature profile of the solid heat capacities and its evolution over time is shown. Up to a simulated time of 0.25 hours, pressurization takes place and the molar flows are established in all passages. Up to a simulated time of 2 hours, constant pressure levels remain and we have slightly rising molar flows. This operation procedure leads to a slow and simultaneous cool down of the heat exchanger solids. This is used in order to avoid temperature imbalances in the heat exchanger solids and to avoid thermal stresses acting on the equipment. The second phase of the startup scenario is the condensation of the hot process streams CLOP and LNP. On the left-hand side again we see the normalized molar flow and the pressure evolution of over time in the single process stream passages. On the right-hand side the actual temperature and heat transfer coefficient profiles at selected time points are shown. As you may notice, CLOP enters the heat exchanger at the left end and leaves the heat exchanger midway through. The flow direction is from left to right. LNP enters the heat exchanger midway through and exits at the right end. Flow direction is again from left to right. The cold GN and CGN passages enter at the right end, leave at the left end, which means we have a counter-current flow orientation. Let's start the simulation. At the beginning, all process streams are vapor only at a time of 1.9 hours. If we continue simulating, after a time of 2.2 hours, the GN inlet temperature has dropped down, which led to a further cool down of the heat exchanger. CLOP and LNP passages are partially condensing, partially vapor at this point in time. Between the high heat transfer coefficients of the two-phase region and the low heat transfer coefficients of the single-phase region, we have a smooth transition which is due to the applied heat transfer correlations. Let's continue the simulation. You will notice that the CGN temperature drops down in addition to the GN temperature. Furthermore, the inlet temperature of the CLOP passage has changed and has dropped down and risen again. This means that the heat transfer coefficients of the CLOP passage have changed too. If the temperature dropped below the bubble point, we had a single-phase liquid CLOP passage with low heat transfer coefficients. At this point in time, we now have a two-phase CLOP passage with high heat transfer coefficients of the two-phase region. On the left-hand side, we can observe that the molar flows start to rise after 4.9 hours of simulated time. The rising molar flows do not have significant impact on the temperature and heat transfer coefficient profiles. This is due to the fact that the ratio between hot and cold heat capacity flow rates does not change significantly. After a simulated time of 7.9 hours, the CLOP inlet temperature started to drop down. This means that the bubble point is present within the CLOP passage and moves towards the hot end of the heat exchanger. Furthermore, after 7.9 hours of simulated time, we can observe changes in the gradients of the molar flows. Let's continue the simulation. We will stop it again after approximately 10 hours. We will notice that we have significant changes in the pressure levels at the passage inlets. Those changes in the pressure levels have been due to liquid buildup in the rectification section of the ASU. The molar flows reach a local minimum after 10.5 hours of simulated time. The CLOP flow almost vanishes at this point. This means that the CLOP temperature is close to the wall temperature. If we continue simulation, after 11.4 hours of simulated time, the molar flows have recovered again. The pressure levels have stabilized and the temperature difference between CLOP and the wall has been re-established. Let's continue the simulation again. We will see the molar flows being adjusted. There is no significant impact on the heat transfer and temperature profiles on the right-hand side again. We will stop the simulation after a simulated time of approximately 15.9 hours again. At this point in time, you will notice that the LMP inlet temperature has dropped down slightly. This means at this point in time, the LMP passage is partially condensing with high heat transfer coefficients and partially liquid with low heat transfer coefficients. The bubble point, which is the discrete jump between high and low heat transfer coefficient, moves towards the left end of the heat exchanger. If we continue the simulation further, all process streams are in the single phase region, which means that we are slowly approaching the steady state operation of the heat exchanger. We'll stop again after 7.3 hours of simulated time. At this point, we will soon see disturbance of the molar flow in the C-lob passage, which arises from a level controller action in the rectification system of the ASU. The temperatures and heat transfer coefficients in the left half of the heat exchanger are affected as the C-lob passage is present there. Let's continue simulation and observe the controller effects. After the C-lob flow has leveled out again, we are slowly approaching the steady state of the heat exchanger. The only thing that is changing anymore up to the final simulated time of 22 hours are the molar flows on the left-hand side of the graphs. After 22 hours, we end the simulation for today. In the end, I will give a summary and an outlook. We introduced a generic and modular first principle model of heat exchangers, which is the core component of a digital twin. It utilizes design correlations for heat transfer and pressure drop. There's the possibility of multiple solutions within a finite volume which suffers a phase change. Therefore, advanced solution algorithms are required and have been developed at Linde Engineering. The case study of the startup of the air separation unit subcooler utilized the digital twin. Potential future applications of the digital twin are process and equipment simulation and optimization, smart plant and equipment operation procedures, online monitoring, hazard analysis, lifetime estimation of heat exchangers, and of course data reconciliation purposes. In the end, it's up to me to thank you for your attention, and if there are any questions, I will be pleased to answer them throughout the Q&A session, which is scheduled on Wednesday.